describe the equations that define the characteristic curves of the transistor that we saw in the previous part of the lecture. And we'll start with cutoff. So for a MOS device in cutoff, we start assuming that the gate-to-source voltage is less than our threshold voltage, or what we'll label V little t. Now note, V little t is not equal to V big T, where V big T is the thermal voltage. And is approximately equal to 26 millivolts at room temperature. V little t is the threshold voltage. So for our MOS device, we'll look at our cross-section, and we'll just draw a simple cross-section. So here we have an NMOS device where we'll start with a P- substrate material. We'll have two N+ regions that will define the source and the drain. And then we'll have our gate contact, which is separated from the channel by silicon dioxide, or an oxide layer in the generic case. Now here, what we've expressly said is that we put a gate to source voltage VGS, so this will be our source contact. This would then be our drain contact. We'll put a gate to source voltage that's less than the threshold voltage on the channel. In this case, the drain to source voltage, VDS, doesn't matter. If the gate to source voltage is less than the threshold voltage, then we have no carriers in the channel and current can't flow. Now, this is just a model. It's not entirely true. In fact, as we increase the voltage, some current will flow, and that current would be called subthreshold current. But for the time being, we'll ignore this. So what we're saying here is that the device is off. So if we look at our transistor circuit model, we have a gate to source voltage that's less than the threshold voltage, and we would say that no drain current flows, or ID is equal to 0, and because we have an insulator between the gate and the source, we know that I gate is equal to 0. Now, what's becoming more problematic in semiconductor, in fine line CMOS processes, is that the gate oxide is so thin that you can get carrier punch through, which would mean that the gate current is not equal to 0. But this is a second order effect, and again, we'll ignore it. Now, as we start to increase the gate to source voltage beyond the threshold voltage, we enter our linear or triode region. So we look at our same cross-section. We have our gate to source voltage. And now we're going to say that the gate to source voltage is going to be greater, and actually the gate to source voltage minus the threshold voltage is going to be greater than our drain to source voltage, which are both going to be greater than 0. In other words, our gate to source voltage is greater than the threshold voltage. What happens here is we have our P- material, which is mostly doped with holes, but there are some electrons in the material. And as we increase the voltage on the gate, negative carriers are drawn up towards the surface of the silicon to oxide interface. And they're done so because of an electrostatic charge. In other words, we put a positive voltage on the gate, so it's going to cause negative ions that are in the substrate to draw towards the channel. This process is known as inversion. If we start to draw enough carriers up and then increase BDS to be above 0, a lateral E field causes a current to flow. In other words, it causes these electrons to be moved towards the drain. In other words, meaning that we have a positive drain current flowing between the drain and the source. So we make a couple of assumptions. One, that the current is due to mobile charge carriers in the channel. The vertical E field caused by the gate to source voltage is what creates that charge. And the velocity of the electrons that are moving in the channel in the case of the NMOS are proportional to the lateral electric field. We know, or we're going to look at the charge density in the channel, Q sub y. Y is defined as the positive direction between the drain and the source terminal. So we know that Q sub y is equal to the capacitance per unit length in the channel, Cox, where Cox is defined as the relative permeability of the channel divided by the thickness of the channel, where thickness is just the thickness of the oxide. So our unit charge per length of the channel is the oxide capacitance times the voltage across it, which would be the gate to source voltage minus the threshold voltage, minus the potential at any point in the channel, or what we'll call V sub y. So whatever the potential is at any point in this channel is what we're looking at. In other words, the charge is the capacitance times the voltage difference across the capacitance. Now we know that our current is equal to the charge density times the width of the channel. So if we were to imagine this going into 3 dimensions, the width of the channel would be this dimension, times the velocity of the particles. And we know that the lateral electric field sets the velocity, so we can say that the current is equal to Q sub y, or Q of y, times W, times a parameter mu, which is mobility of the carrier in the channel, in this case the electron, times the E field.